Knowing how to calculate odds is very important if you're going to gamble. In the long run, you're probably going to lose. The house has to have an edge. They have to win more than they lose in order to cover their costs and make a profit. But at least if you know how to calculate decimals and fractions, you'll lose more slowly. You're giving yourself a little bit better chance than just going for blind luck.
Ken, this may not be your game.
We can't avoid risk. That's true of individuals, it's true of firms, and it's true of governments when they make investment decisions. Here we are at Stonehenge, a World Heritage Site, and there's a road which passes by Stonehenge and is the main route down to the West Country. The government has to make a decision about upgrading the road. One possibility is a 2-kilometre tunnel which would preserve the site and get rid of some of the noise pollution and the air pollution which results from the traffic. So if the government is going to build a tunnel, how big should the tunnel be? At the moment we have a road where part of it is single lane, part of it is double lane. One possibility is to build the tunnel with 2 lanes in each direction. But at some stage in the future, it may well be necessary to upgrade this to a 3-lane motorway, in which case it would be sensible now to build 3 lanes each way for the tunnel. But that's going to be more expensive. Is it worth the extra cost? Clearly, a significant part of the answer is it depends upon traffic growth. The faster the traffic growth, the more sensible it would be to go for the 3-lane each way option. But we don't know how fast traffic growth will be in the coming years. How do we use our understanding of risk to maximise our chances of getting it right?
To do that, we need to distinguish risk and uncertainty. Risk means that we do not know the future, but we do know the likelihood of the various possible outcomes. With uncertainty, we do not know the likelihood of each outcome.
If we toss a coin, is it going to be heads or tails? We don't know, but we know that with 2 possible outcomes, there's a 50% chance it'll be heads and a 50% chance it'll be tails. If we know the possible outcomes and we know the probability to be attached to each one, we call that risk. Now let's suppose we toss a coin that we know to be biased, but we don't know how. We again know the possible outcomes. It's going to be heads or tails. But we don't know the probability to be attached to each of the possible outcomes. So if we know what the outcomes are going to be, but we don't know what the probability is to be attached to each one, we call that uncertainty.
Armed with this distinction between risk and uncertainty, let's consider the question of how many lanes are needed for the tunnel that bypasses Stonehenge. So here we're going to use fractions and decimals to help us to make sensible decisions as to whether to build a 2 or a 3-lane tunnel around Stonehenge. Let's start off by assuming that we're in a situation of risk. That means that we know the probabilities of each of the possible outcomes. Here we have 3 possible outcomes. Possibility X if there's high traffic growth, possibility Y if there's medium traffic growth, and possibility Z if there's low traffic growth. We know the probabilities to be attached to each of these possible outcomes because we're in a situation of risk. So there's a 50% chance that we'll have X, a 30% chance that we'll have Y, a 20% chance that Z will turn up. And we're trying to decide whether to build 2 lanes or 3 lanes. Now, what are the numbers that we've got in the boxes? These numbers represent the assumed net benefits to the community of choosing these options. That is to say, we've made an estimate of all the costs of constructing the roadway. We've made an estimate of all the costs of building the motorway. We've made an estimate of all the benefits, and we take the costs from the benefits and we're left with the net benefits. So the numbers in the boxes represent the assumed net benefits. We don't have any actual benefits because no one's done the calculations, but we're interested to know how we would proceed if these were the appropriate numbers. So what would we do when we don't know whether outcome X or outcome Y or outcome Z is going to turn up? Well, we calculate the expected benefit from decision A, the dual carriageway, and the expected benefit from B, the 3 lanes. Let's take A first of all. We could say there's a 50% chance that X will turn up, so we'll take the net benefits 6 and multiply them by the probability of a half. And then we'll add to that outcome Y's possibility, 9, multiplied by its probability of turning up, 3/10. And then add to that the benefits of Z, but we'll multiply that by the relatively low probability of 2/10. So we add up a half times a 6 plus 3/10 times 9 plus 2/10 times 15, and that gives us £8.7 million worth of net benefits. So we can say that that is the expected benefit of doing A. We'll perform a similar calculation for the expected benefit from doing B. This time there's a 50% chance that X will turn up again, but this time the expected benefits are 12. So a half times 12, now look at Y, plus 3/10 times 9. Now look at Z, plus 2/10 times 6. If we add all this up, we get 9.9. So the expected benefit from doing B is higher than the expected benefit from doing A. So under these assumptions, we would do B, the 3-lane carriageway. We might live to regret it. We might get it wrong. But it's the best calculation we can make, given that we know the probabilities of each of the possible outcomes. Now let's assume that we're not in a situation of risk, but we're in a situation of uncertainty. That means that this time we don't know the probabilities to be attached to X, Y, and Z. We don't know whether one of these possibilities is more likely than the others. What do we do now? Well, one way to proceed is to use what's called the principle of insufficient reason. If we don't know which of these outcomes is more likely than any other, we have no sufficient reason for thinking that one outcome is more or less likely than the others. So we'll attach an assumed probability of 1/3 to each of the possible outcomes. So if we do that, we can now rework our calculations on this assumption. The expected benefit from A is now 1/3 times 6 plus 1/3 times 9 plus 1/3 times 15. If we add that up, we get an expected benefit from doing A of 10. Similarly for B, we take 1/3 times 12 plus 1/3 times 9 plus 1/3 times 6, and that gives us an expected benefit from B of £9 million worth of benefits. This time, using the principle of insufficient reason, we would decide that the better option is to stick with the dual carriageway. because the expected benefits from A are higher than they are from B. Now, using these procedures, there's no guarantee that we'll always make the right choice. That's the essence of uncertainty and risk. But we do now have a rational way of proceeding, and the rational way of proceeding requires us to understand fractions and decimals.